Hey guys, I'm gonna go over two topics from Reci just to hopefully give you guys a better, idea of what it is. And the first of them is the origins of replication. So, origins of replications are essentially areas in which replication begins. So, in eukaryotes, there's multiple origins of replications during DNA replication, and in prokaryotes, there's only one. So here, let's say we have. Here we have a DNA strand. These are here are origins in which replication begins. And you're going to have DNA polymerase, and it's going to go in two directions at each origin of replication. So it's bidirectional. So the way you would go to solving a problem like this, if you were given one, first you'd have to read and understand what the problem is asking for. So the problem says the genome of D. melanogaster consists of approximately 1.7 times 10 to the 8th base pairs. DNA synthesis occurs at a rate of 30 base pairs per second. In the early embryo, the entire genome was replicated in 5 minutes. How many bidirectional origins of synthesis are required to accomplish this? So let's write down the information we're given. The entire genome is consistent of 1.7 times 10 to the 8th base pairs. DNA synthesis occurs at a rate of 30 base pairs per second. And it takes a total of 5 minutes to replicate the entire genome. So, with the information we're given, what we would first need to do is we would take the amount of base pairs per second. That's the first step. See the base pairs per second, which is 30 base pairs per second, and we would multiply that by 2, because from this picture we can see that DNA synthesis and DNA replication, it occurs in two directions. It's going one way and the other way at each origin. So that gives us 60 base pairs per second. Then what we need to do is we need to take the base pairs per second and we need to multiply it by the amount of time it takes to replicate the entire genome. So it takes 5 minutes, so what we would do is we'd do 1 second. Wait. We have 60 seconds per 1 minute times 5 minutes. And that would give us 18,000. So this is how many base pairs are coded for per origin of replication in 5 minutes. So now all we need to do is we need to take the total amount of base pairs in the genome divide it by the amount of base pairs coded for each origin in 5 minutes, and that gives us roughly 9,444 origins of replications. So it would take 9,444 origins of replications that would code 18,000 base pairs to code the entire genome in 5 minutes. On to the next question, or the next topic, which is question 10 of the practice problems. A lot of people seem to be confused on this, so hopefully we're going to remove some of that confusion. So the question is asking, where it says that you are working on breeding strawberries and know that there are two loci that affect the susceptibility to fungal pathogens. You have identified alleles associated with higher fungal resistance at both loci. The R locus has two alleles, wild type and R, with R conferring higher resistance. The F locus has two alleles, wild type and F, with F conferring to higher resistance. Question A is asking, where it says, if the loci are on two different chromosomes, what would be the genotype of an individual that is heterozygous at the R locus and homozygous for alleles conferring higher resistance at the F locus? So question A says that they're both on different chromosomes, or if the loci are on different chromosomes. So when questions are being asked and it says something's on the same chromosome, what they're referring to is something on the same homologous pair. So these are here homologous pairs, meaning that each chromosome is essentially the same chromosome. One's given from your mother, one's given from your father. The only difference comes in at the alleles. So the alleles may differ in DNA sequences or nucleotide sequences, but they code for the same gene overall. Let's say that this right here is a maternal gene. There's a chromosome that's maternal, and this is a paternal chromosome. And these right here are on chromosome 1. This is chromosome 1. Now at the maternal chromosome, let's say we have the mutation, which is going to give you the R allele. At the paternal chromosome, let's say it's going to be the wild type allele, which is going to have no resistance. Now the way you would write this is R chromosome, so this right here stands for this. Now we'd write chromosome plus, because this right here, the little line stands for the chromosome. In shorthand notation, this would become R dash plus. Now, going on to chromosome, the different chromosome, which carries the F gene. Since it's on a different chromosome, let's say this is chromosome 2. So a completely different homologous pair. At this location, or this locus, we have 2 F alleles. So since it's homozygous recessive, we just have F and F. Now the way we would write this down is F chromosome chromosome F, or F dash F. Now to correctly write this, we would just put down what we wrote up here, or the chromosomal format, with a little semicolon, and this indicates that it's on separate chromosomes, then F and F. So this would be the correct way to write it. On to part B. Part B says that if the loci are on the same chromosome, write down the 2 locus diploid genotype of an individual plant that is heterozygous at both loci and will pass on chromosomes that carry only one allele that confers high resistance to its offspring. Okay, so they're both on the same chromosome. So now, let's say they're both on chromosome 1. So they're both heterozygous. So if we were so at the R locus, let's write an R wild type, F wild type. Now if we were going to write this down, we would just read the chromosome. So on this chromosome, we have an R, and then we have an F. On this chromosome, right here, we have plus and a plus. Now this would be the correct way to write it down, but the question is not asking for it to be written in this format. The question says it wants it so that each chromosome will pass on an allele that confers higher resistance. So when these separate during meiosis, each of these chromosomes, we're going to get a chromosome that has both alleles for higher resistance and a chromosome that has no alleles for higher resistance, which is not what we want. The question wants each chromosome to have an allele for higher resistance. So instead, what we need to do is we need to erase one of the alleles at one of the loci. And we just need to swap them. Put a wild type here and an F here. So now, we would write R, over here R, plus, and for this chromosome we'd write down plus F. And if we were going to write it down in shorthand notation, it would be R plus F. Now I've seen some people write down R plus F plus. Now if we were to, now this would be incorrect. Now if we were to expand on this, we'd find that if we wrote it down in the longer notation, we get R plus, chromosome F plus. But if you look closely, you can see that the R and the F are on the same loci. They're on the same area relative to each chromosome, which would mean that if I was to turn these into chromosomes, or if I was to do something like this, perhaps this will be an easier way for people to see it. Right here, if I was to flip this 90 degrees, it would end up looking something like this. So right here, the R allele corresponds to the F allele. It's on the same loci, the same location. And what you're doing at this point is you're swapping alleles for different genes and putting them together. So this allele, the F allele, does not go in the R locus, and the R locus should not have an F allele. So that's why writing it in this format, where it would be like this, is incorrect. You want to have the alleles relative to the chromosome, or both the alleles relative to each other on the different chromosomes. So if I have an R allele right here, I would want the corresponding allele to be on the same area. Here I have an F allele. I want the corresponding allele to be in the relative area. If this right here was another F, I'd want this F to be in the same relative area on the chromosomes as this F is.